Good morning, everyone. Welcome back. So, we have been talking a lot about the interaction of the converter with the grid side, whether DC or AC, in the past couple of days. We did not talk a lot about aspects on the DC side, so to speak. If you have an inverter, let's say, that connects the DC side to the AC side, the control and support of this voltage. So in this class, I'm going to talk about that aspect. So we would like the control system also to control the voltage on this side or to provide support to this side, because this could be other entities connected to this terminal and they all benefit from the voltage at this terminal. And we would like the converter to support the voltage on that side as well. So if you look at the support, again, you can define two types of support, static support and dynamic support. The static support is proportional to the offset of the voltage around its rated value, and dynamic support is proportional to rate of change of the voltage. All right. So in order to go a little into details of this and design controllers for that aspect, first of all, we notice that as far as the power of the capacitor is concerned, we have the voltage into the current, which is this equation, and its derivative of the energy that is equal to power coming to a capacitor and power leaving the capacitor. So the difference of that is the power that goes inside the capacitor, and that will be derivative of its energy. Energy is half CV square. So basically, this is a structure we have. We would like to now look into details of this voltage, control and support for this voltage. So basically, what we had in the previous classes was that M into Vc generates the voltage across these terminals here, and this voltage minus this voltage divided by this impedance is the current. That's basically what you get here, and that little resistance could be there. Now, this current multiplied into this voltage is the power output of the converter, which is at this point. Now, if we ignore the tiny amounts of power losses happening from here to here, we can approximately say that this power is also equal to this one. And then P in coming from the previous stage, look at P in as a disturbance for now. So P in minus this power is the power going to the capacitor. So I into Vg, that's the output power. P in minus this one is the power of the capacitor. Integral of that becomes energy. From energy to voltage is a nonlinear function that goes through that and comes back. So this diagram here, based on what I just described, gives you a full description of the mathematical model of this system if you are interested to control the dynamics of capacitor voltage. Okay. Now, this looks like a complicated model because, first of all, it has a nonlinearity here, possibly a nonlinearity here, and things of this sort. Let's see what we do practically to deal with this model. First of all, it's a very common practice, as we already mentioned before, to have this linearizing feedback at the beginning input of this system. So we add this division to cancel this multiplication. And then also a feed-forward term. And we are talking about AC systems. That feed-forward will be Vg passed through PLL and then coming here. If you apply these two, what happens is that these two cancel each other. Suddenly they go away. and this cancel each other. What remains? Only harmonics remain, because fundamental cancels. PLL provides the fundamental component. So the block diagram simplifies a little bit to this diagram. So by using some initial feedback procedure, you can simplify the block diagram. Now let's talk a little bit about this P in first. This P in is the power coming to the capacitor here. It really depends on this side. What is this side? So unless I know what is this, I cannot say much about P in. For instance, if you have only some panels here, solar panels connected here, so that power is the power coming from solar panels. It has a nonlinear relationship with the voltage, as you all know. So that you can say it has this relationship. This is the case that you have solar panels. So the voltage goes through PV characteristic, that nonlinear characteristic of the PV, and that gives you how much power. So then P in, or the input power, is not independent from your feedback loop. It actually depends on your feedback loop. And if this is the case, we cannot consider that as a disturbance, because definition of the disturbance is a variable coming from outside, not from inside. Right? So this is when you have panels directly connected to this capacitor. If you have some panels connected to this point through a converter or other resources, batteries, whatever, connected to this point but not directly, through their own converters. So in that case, they have their own controls and then send the power to this capacitor. They do not watch this voltage necessarily. They just do their own control and send the power. In those cases, you can say this input power is independent from what we are doing. And then really we can consider that as a disturbance. Now, if we want to follow the strict mathematics and control, we have to follow this diagram for PV, for instance. But this is a nonlinear characteristic, already a nonlinearity here. It becomes too complicated. What we have done is that anyway, whether it's coming directly from a PV or through other converters, we treat this as a disturbance. In other words, we just leave it as an external input coming here. And then we design a controller, and that controller, we try to design it robust and stable and strong. And using simulations and everything, we will show that the closed loop feedback that we will design will respond to all uncertainties, all disturbances, all changes in a strong way. Okay. So again, one more time, the equations of this system. We have omega c, that's the energy. Derivative of that is P in minus P out. P out is Vg into I, and I dot is this one. So this system has two equations. It's still not linear. And even if you consider Vg, the grid voltage, as an external signal, which is an external signal, normally the converter does not control that voltage. In this case, if it's connected to the grid, so it's a grid voltage. So if you consider that as an external waveform, then this is linear, yes, but not linear time invariant, because this is a time varying waveform. So it's linear time varying system. We cannot use Laplace transforms and those things to simply or directly analyze this system. Okay, let's see how to go around this problem and then eventually design a controller for this system. What we do, obviously, we always want to keep in mind that we want to do current limiting. So a current feedback loop should be there. That's the current feedback loop here, in order to be able to limit the current. So this is the limiter for the reference. and then current feedback loop. And then this has two inputs, one ID and one IQ. ID represents the real power, IQ represents the reactive power. Remember, we are in AC domain now. So ID, which represents the real power, I'm going to determine ID, reference for ID, according to this mechanism that we already used this before, which is I0, I naught, the rated current if you want, plus K0, VC minus, again, the rated voltage for this capacitor. So I'll explain a little bit why this means. And IQ represents the reference for reactive power. You can put it 0 if you want if you want no exchange of reactive power, or you can put it any number that you want, depending on how much reactive power. Or if you want to bring it from a Drup form, you can do that. So basically, from the energy, here is energy. We linearize the energy function. We have linearized it before. So this is the linearization of the energy to the voltage, this part. And the voltage goes back here, feedback, and then the current feedback loop. So this part we have already designed, and we know how to do it perfectly, no problem. K0, let's discuss this equation a little bit. This basically says, not a Drup equation, but it's kind of a rise equation. That means that when the voltage of capacitor goes up, it increases its current. So this capacitor says, and remember, the current is going from the capacitor to the grid. When the voltage goes up, it provides more current. So when the voltage goes up of the capacitor here, if you look at this structure, the power is coming. We decided to look at this power as disturbance, so we are not going to measure it. We are not going to focus on it. We just watch this voltage. When this voltage goes up, it is an indication that more power is coming. Then the converter uses that as an index, as a measure, as a flag, to send more current to the output. As simple as that, in a linear manner. So when this voltage goes up, it sends more current. The more it goes up, the more it sends more current. So this is really a static support, the same equation that we had here. It says the voltage goes up, send more power, right? So it implements basically the same static support that we just said. And the parameter K0, you can easily design based on how much you want this voltage to go up or down for the entire range of your operation. Let's say this voltage is supposed to be 400 volt. The converter is supposed to operate from 0 amperes to 20 amperes, but you would allow the voltage to change 20 volts for the entire range. So the voltage changes from 400 to 420, or from 390 to 410. It's up to you to choose. So based on that alpha, which is how percentage you would allow your voltage to go up and down, typical numbers anywhere between 2, 3, 4, 5%, even maximum 10%. But 5%, in my experience, is a very good number. So alpha is chosen, and then from alpha you find K0. So K0 is designed based on this steady state requirement. And the parameters of the current control loop, we already discussed in detail yesterday how to design that. Okay. Now, in terms of analysis, a little bit more into detail, this diagram also gives a lot of insight into this, what's happening into this system. Really, if you look at that linear time varying term that I said it causes an analytical problem, if you look at I into Vg, I has two components, direct and quadrature, and voltage is only direct. You multiply them, you will get a DC here, and then an AC here. So DC and AC. Now, if you want to show that on the diagram, I'm going to substitute this diagram that we had here, this multiplication here, based on this equation. So that means this ID multiplies into VG over half, plus this part. What is this part? S into cosine of 2 omega t plus phi. So it's like there is a DC coming and suddenly a double frequency is injected into that at this point. And then coming here, this is the input power. We assume it's disturbance and DC, and everything else is DC so far. So this double frequency is injected here. This double frequency is injected here, and it will propagate all throughout the loop. It will go to the capacitor voltage and will go back all the way to ID. If you want to see how much it will be in the capacitor voltage, this is multiplied into 1 over S, which is 1 over 2 omega at that frequency, into C. So that means how much will be the double frequency here. This equation we derived at the beginning of the previous class with another way of looking at the problem. So the same equation now we derived here. And if you want to, and by the way, this voltage, double frequency voltage on the capacitor, if you see, is completely a physical component. The control cannot do anything about it. It depends on power, it depends on the capacitance, it depends on the frequency, it depends on the capacitor voltage. No control parameter is here. And that makes sense. It's a physical, aspect of the system. However, if you look at this double frequency coming back here to ID, that multiplies into K0. So that is the double frequency ripple on ID. And ID is the D component of the current, or real component of the current, will eventually go to appear as a harmonic. If you have this double frequency here, double frequency in D will be a third harmonic in the current. So that we care about. We don't want that to be too much because the current becomes distorted. How much is that? That's VC2 into K0. And now the control parameter appears. K0 is here. Okay. So what I'm going to define percentage ripple current, I'm going to define ID2 divided by I multiplied into 100. And I would like to keep that small. So this RP, I derived an equation for it here. So this K0 that we started with by designing it, or determining it, how much voltage change we would like to have, we also should watch it. If it's too much, then it will cause too much harmonics on the current. You have to make a trade-off. So let me summarize everything in one algorithm. This algorithm here. The grid voltage is given, the frequency of the grid is given, the power rating of the converter is given. From power rating and the voltage, you can calculate the current rating, no problem. Capacitor voltage should be given. You should decide how much you want this capacitor voltage to be. 500 volt, 400 volt. Range of capacitor voltage also you need to decide. If it's 500 volt, and then you would not mind if it goes up and down 5% around this 500. So you choose that one, alpha percent. And then you should also decide how much harmonics you can tolerate. 1%, 2%, 3%, RP, that is all. And then you can calculate the required amount of capacitor and the control parameter K0 from the equations that we just discussed, 647 and 649 here. This is for the K0, and then 647 here. So you find K0 here, and C from this equation. So basically, here I looked at the problem, or as the parameters that we want to design as K0 and the capacitance. In other words, this algorithm tells you how much is the minimum capacitance that you need in order to satisfy this amount of ripples and this amount of, yeah. Okay, there are some little details, but these are secondary. You can read later on your own. I don't want to spend too much time on them. Let's look at this example. Let's say for the same system that we had, 500 volt capacitor, we would like to have to allow 5%, which is 25 volts. And also 5% of the double frequency ripple on the current. Then you will calculate K0 from that equation, and that will be 0.47, and you calculate the required capacitance, that is 4.2 millifarad. This is basically the minimum capacitance that you need. Okay. Then the voltage double frequency is 1.8 volt. This does not depend on control parameters, no problem. And then, so K0 is there. The other parameters for the current control loop we already designed. We only needed to design K0 and capacitor. Now, if you look at this simulation here, which I'm going to run in a moment in the computer also, shows a scenario that first, obviously, when you have a DC-AC system, as we said before, you start the PLL at t equals 0. You wait sufficient time here, about 50 milliseconds, for the PLL to converge, and then start switching the converter. If everything is done well, you should have a soft start. Like here. So then a little bit later, here at 0.1, we have jump of real power command. So real power from 0 to 2 kilowatt, and the current starts building up. And the capacitor voltage goes from 5% below now to 500. So when it's not feeding any current, it's at the lower value of the voltage, which is 475. And then when it feeds full power, it will go to 500. And the current now goes to the rated current here. And then you can check reactive power, positive and negative, which looks like it's responding very well, very smoothly. And here we have a grid voltage. Say this is grid voltage, deep fault at this point. And the current should be limited at, I'm not sure, 20 or 22. 22, I guess that was our limit. So the current keeps going up and limited at 22. And capacitor voltage, obviously, during the current limiting mode, because the power is coming from the previous stage, and the inverter cannot supply much power to the grid because its current is limited. So this difference of power will go to the capacitor, and capacitor starts charging. See, the voltage of the capacitor keeps rising during the fault. Here the fault takes only a few cycles, and the capacitor voltage rises from 500 to 520. So this is also another criterion when you want to choose the capacitor, which we haven't discussed here. How long the faults happen in your system. If you really have faults that take long time and you want the converter to keep working during those times, still operating, then your capacitor should be large enough such that it can accommodate this amount of excess power coming in it without its voltage going too much high. And then when the voltage goes back, now the capacitor releases power and goes back to 400. And here at this point, we have a set point change. We ask the converter to change the voltage of capacitor from 500 to 520. And it does, right? This shows the THD, total harmonic distortion of the current. Remember, we chose RP equal 5%. That is the reference of the current. We allowed 5% distortion, double frequency on it. And I said it will convert to harmonics on the AC side. And obviously, it goes through the current feedback loop because ID is before the current feedback loop. It goes through the current feedback loop. The current feedback loop also works on it. So for that reason, on the output, you do not get exactly 5, but you get below. So current feedback loop reduces that a little bit. So about 3 or just over 3% THD you see at the output. Okay, so let me run the simulation. You can also open the M file. I want to close that. So that is THD. I think I have this. Ah, So the circuit, if I want to explain a little bit while it's running. Here is the power circuit. As before, you have one capacitor here and a power coming from the previous stage. And again, this to me is the convenient way of modeling. Use a current source and power divided by the voltage. That will be the amount of current coming. Whatever power you want to assume coming from the previous stage, put it here, and then divide it by the voltage, and then apply that as the reference to this current source. That will cause this current source to generate the voltage here, to generate the power here. It's running now. Okay. So here is when you apply the real power command of 2 kilowatt. So this is the command, and this is the actual power. And I think this is the reactive now. And this is the reactive command and the reactive actual. So to 2 kilowatt. And then now reactive goes to negative 2 kilowatt. Very extreme sudden change. So it will cause an oscillation on the real power as well. Then go back to 0 for the reactive power. So during all this stage, the capacitor voltage is this one. So at the beginning is 475, then goes to 500, and then remains around 500 as far as the power is full power. Here now it's going through the fault. noises. And then fault is cleared, so comes back to 400, 500, sorry. And then the command of 500 to 520 is applied. It's up there. THD is shown here. So 4% or below 4%, close to 3. And the current. This is the reference of the current is the blue one, which doesn't have switching noises, and the yellow one is the actual current, which has the switching noise on it. It's pretty much sinusoidal, but we know it has a 3% THD, harmonic 3. If you observe it closely, you see that it's not clearly sinusoidal. All right. So the control part, control part, pretty much what we had before. This is the PWM part. This is the current controller and limiting that we, current controller, the limiting is here, and the PLL. All right. I opened the code. I think I opened the code, but maybe that was it. All right. The code is also here, but I don't think we need to run it because already this code basically runs the simulation file. These are the design aspects which is done here. The current controller was already designed in the previous example, so it is not redesigned. Again, the same numbers are used. And then after it runs the simulation, it generates the figures that I had, the only figure that I just showed you. This figure. All right. So that was the aspect on the DC side. There are more details, but really I wanted to cover the foundations and the most important aspects. Now, we discussed the grid-connected case and feeding power to the grid. We also talked about grid support in details. But we did not talk about load voltage control and support. This is the case that you have a load here, and then you want to control the voltage of the load. And obviously, we want to satisfy the other conditions like limit the current and should respond to the variations in the load in a quick and a smooth manner. These are the control objectives, robust. But we would like to have a voltage which is sinusoidal at the given amplitude and a given frequency. Okay, the mathematical model of the system is very simple. M into Vc, that gives you this voltage. M is the input, which is modulation index. And that V minus this V, which is the output voltage that we want to control, divided by this impedance gives you this current. And this current minus the load current gives you the current going to the capacitor, and integral of the current capacitor becomes the output voltage. And this goes through the load. So this is the mathematical model of that. Now, normally we don't consider load in our control designs. You may want, if you have good information about load, you can consider that in your design. If you don't have it, just completely ignore it. And then look at IG as a disturbance. Remember, we just did the same thing for PV, and we said if the controller is strong, it doesn't really mind. It will be able to tolerate it. So if you don't have much information about the load, or you don't even want to bring those information into a study, you can just completely ignore this load and consider this point as a disturbance. Then our objective is to control the voltage. So one initial approach would be, I would like to have a sinusoidal voltage here. Let me put a resonant controller because it's sinusoidal and it has two gains, and I have two other state variables here, one current and then one voltage. The system has four state variables and then feedback all of them, K1, K2, K3, K4, full state feedback. I will use a a linearizing term at the beginning, at the input, to cancel this nonlinear term. Then everything is linear time invariant, and I can use optimal control to design K1, K2, K3, K4. No problem. So that's what we do. And then this voltage reference is the sinusoidal voltage that we want. So we want the voltage to have this magnitude and this frequency. So you integrate the frequency, that gives you the phase angle, cosine of that multiplied into magnitude, that gives you the voltage. So this is clear. All these gains you find using LQR, and then you should have no problem. So write down the equations, apply the transformation, and then the cost function will have error and derivative of error, and Z3 and Z4 will be the current and the inductor current and the output voltage when you apply the transformation to them. And this W is again the modulation index when after you apply the transformation. So you can start with Q, increase Q, look at the poles, and then if you need be, you can look at Q2, Q3, Q4. The picture that you get typically is something like that. Q will push these low frequency poles to the left, also a little bit high frequency. This system has two, depending on values of L and C, normally L and C are not unnecessarily large because we don't want to spend unnecessarily much on them. So if you choose them right numbers, the frequency that these specify is a high frequency. And then this frequency is 60 hertz, so it's low frequency. That's why you see here two high frequencies. This represents the high frequency, this represents the low frequency, 60 hertz. So Q, when you increase Q, dominantly moves the low frequency terms. Then you go to Q2, also moves the high frequency terms, Q3, Q4. And let's say we stop here. We see all the poles are around negative 800, 1000, around that. These are the typical numbers for this level of switching frequency that we consider here. Switching frequency is only 4 kilohertz, so we cannot go too much. Zoom it. Okay. So eventually we have these 4 poles by increasing Q. And then if you look at the simulation shows very strong responses. The voltage, this is the voltage reference that we want. We want, let's say, 240 volt RMS, 60 hertz frequency. So at this point, the converter starts and then immediately builds the voltage at the output. Almost no transients. See, there is only a tiny transient here. And then immediately, because it's very strong. And then at this point, a load is connected. And the converter increases the current. But the voltage does not really change. The objective is to control the voltage. At this point, a huge load, or you can say a short circuit, or something like of that sort happens at the output. So the converter increases the current to keep the voltage at that thing. So this is the behavior that in the DC part also I went through as an intermediary thing to say this is not a nice approach to do. It's on the paper, it's good, or on the simulation, but in practice, this is not going to work because you have no control over this one, this current. Okay. So what we need to do, we need to do current limiting. If you want to do current limiting, always my approach is let the voltage move a little bit, and then based on the motion or the offset of the voltage, you can define a reference for the current, and then limit that reference, and then close a current feedback loop. So you let the voltage change a little bit from the actual voltage that you want through a virtual resistance. And according to this diagram, see, you get this voltage, and then you let the voltage move a little bit through this impedance, and then to generate a reference for the current. And you can convert, this is AC, you can convert it to DQ, and then you can limit it, and then come back to AC. So remember, limiting should be done in DQ, okay? Because we cannot limit in AC. You do not want to clip the waveform. So you need to convert it, go back to DQ, we discussed before in this figure 634. So you convert it to DQ, you limit it, and then after you limit, you convert back to AC, and then this is current feedback loop that we already discussed, closed on this current. So this is the approach with current limiting. Okay. The only parameter now that you need to design, apart from current feedback loop that we discussed in detail, is this virtual resistance. That virtual resistance basically, again, shows how much you want to this voltage output, how much you would allow that voltage to change, the magnitude of that voltage. Are you happy with 5%, 4%, 3%, or no? So these are the typical numbers, 3, 5, 6%. You don't want that to be too big or too small. Okay. So I think in this case, I went, 20 volt RMS change. Okay. And I believe I did the same simulation that we had in the previous figure. And now you remember when you have the fault happening or the short circuit or huge load connected, the current is limited. I think we wanted to limit at 40 here. So I limited at 40, but because you limit the current, as a result, the voltage drops. The voltage cannot, the reference is high, but the actual voltage drops. This is showing really an extreme case. But in normal case, it will drop just a little bit. And as you go further and further deep into the fault, it will drop more. But at any rate, the current becomes limited. Okay, let me see if I wanted to show this one or no. Yes, I think I wanted to show this as well. All right, so this is the circuit we have. It's an inductance, a capacitance here, and this is our load here. And this is to cause a short circuit. It's not a zero impedance short circuit because really that's very extreme, but here there is a switch that has some internal impedance, and then when you uh, connect this switch, there will be a small impedance, a small resistance that connects this terminal to this terminal, almost like a short circuit. And this switch is to start the load, T load. Okay. The current controller, you see, is exactly the same. This is the reference part, omega 0, integral of omega 0, cosine. Magnitude is fixed, and PWM. Very simple simulation. So this shows the load voltage and the reference voltage and the current inductor and also the current the capacitor. For some reason I showed the current of the capacitor as well. And the THD of the voltage. To show really that the voltage in the steady state. You see those spikes that happen in the THD block, don't worry about those because it's a window which is a sliding, so it takes some time for the FFT to go through one cycle. So ignore all these spikes. This is the value of the THD that matters, which is 3 into 10 to the power of negative 3. So it's basically showing that there is no harmonic at the voltage. The voltage is completely sinusoidal. And the current is limited at 40, right? Don't know which one. Yeah, this should be the current. So this is the voltage, and this is the current. Which is limited at 40. And the current limiting is done here. In this block, if you go in, it should show the limit of the current that we have assigned. 40. So whatever you assign here, that will be the limit for your current. All right. So this is another approach of deriving the grid forming controllers. We talked about VSM yesterday, which is the most common grid forming controller. Yes, and we derived its equation using just looking at dynamic support, static support. We combined them and we manipulate equations, integrated them, and then we derived the structure of a VSM controller. I told you another approach is look at the equations of the synchronous machine, synchronous generator, and try to model them, all the physical components. And by the way, the challenging part is the damper windings. People still have a lot of difficulty modeling the damper windings on the synchronous generator. So that's the difficult part. But anyway, if you manage to do to a certain extent, now all those equations, dampers and other parts of the machine, synchronous reactance, windings. Just implement all these windings in your inverter. It will eventually be very similar to VSM that we had here. But this is another approach. Another approach is here basically says, if you look at this, what I did here in this load control that we just discussed, we said this is the reference of the voltage. We want to have a voltage at a given magnitude and a given frequency. So we generated that here, gave it as a reference. So the converter generates this voltage. In grid forming, the situation is that this converter is connected to some assets out there on the AC side. There could be other converters all connected or other resources. And they all together, they form a grid. So they should not fight, so to speak. In synchronous generators, this is the case, basically. They should leave some room for each other to actually talk to each other and try to work with each other, right? So in other words, you should relax these two things, frequency and magnitude. You should not make it tight. That's this approach. So you say, I go with this approach that I just talked, load voltage control, but I will relax the frequency and voltage. But what do I mean by relax? Again, this could be different ways of looking at it, different opinions, but this is the common way that has been done in synchronous generators. It says the frequency is related in a droop manner to the real power, and the magnitude is related to the reactive power, again, in a droop manner, right? So in other words, the converter says, if the frequency is going up, I supply less power. If the magnitude is going up, I supply less reactive power. In other words, I talk to you. I talk to everybody else. If the frequency at my terminals, which is connected to everyone, so it has an indication of what everybody else is doing, if that frequency is going up, means everybody is supplying more power. Let me reduce the power. They don't need my power. They already have a lot of power. If the voltage is going up, that means everybody is supplying reactive power. They have a lot of reactive power, so let me reduce mine. So this way, you talk to each other in a very stable and inertial manner, so to speak. So this is, therefore, that's the way to implement it, right? P set minus P into Kp plus omega 0, okay? It is also very common to put two low-pass filters for the real power and reactive power. Because real power and reactive power, remember, these are physical quantities coming. You take measurements of the voltage and current, and these are sinusoidal waveforms. They can have harmonics, distortions, all those things. When you calculate real power and reactive power, you need to do filtering. So the simplest filter that you can put is a low-pass filter of order 1. That's the minimum you can put here. Okay? So keep this in mind for a moment. Now let's look at this approach. And this is like mimicking the synchronous machine. Synchronous machine, the main equation that synchronous machine has is called the swing equation. Swing equation is this one. Mechanical power minus electrical power is the inertia power. Or, yeah, inverse of inertia power. So that means if you want to show it in diagram, that is this one. Mechanical power. And the mechanical power, we know on the governor of the synchronous machine, mechanical power is a droop function of the frequency or the speed. So that's the governor operation. That's the governor operation. And then that generates the mechanical power. So this point here represents mechanical power, and this represents the electrical power. So P mechanical minus P electrical, integral of that gives you the speed. And then integral of speed gives you angle, and cosine of angle multiplied into magnitude gives you the internal voltage of the machine. And this is the operation of the AVR, automatic voltage regulator, that basically implements the droop term between voltage and reactive power. So if you mimic the synchronous machine, you will get these equations. The only thing we did not consider in these equations is the damper windings of the synchronous machine. Like I said, that's the difficult part. Okay, now I'm going to prove, and this should be nice for some of you if you are doing research in this area. I'm going to prove that this diagram, and you remember how we derived it, and this are mathematically equivalent. There is only a tiny amount of difference between them, and I will show you what that is. So it has really theoretical value, this analysis. And it's not difficult, so let's find. If you write the equations for, let's say, this is 686, the previous one is 685. In 685, equation for the frequency is this one, and then convert it to time domain, you will get this equation. Now you come to this diagram and again try to write down the equations, first in the Laplace domain and then convert it to time domain, you will get to this equation. Look at these two equations. They're exactly the same. Only some parameters renamed. But other than that, these are exactly the same equation. So you can always adjust the parameters to make sure that these two equations are exactly the same. However, when you go to the magnitude equation, for the previous diagram, you will get this one. And for the other one, based on synchronous machine, you will get this one, which you will see its great resemblance between the two. But not exactly, you cannot see that exact equivalence because this term V and this term VG here, V represents the internal voltage, VG is the grid voltage. So in one of them is the internal voltage, in one of them is the grid voltage. So that's a small difference. What is the consequence of that difference? I haven't studied. I don't think anybody has studied. But what basically it showed that a lot of people talking about droops, a lot of people talks about virtual synchronous machines, swing equation. It's basically the same thing. Right? The differences, if any, they are minor. Okay. Now, one thing we haven't talked about is the damper windings. Damper windings, the way we implement, and this is again an area of very active research. Because physically we have difficulty modeling damper windings, so people come up with ideas how to model different ways. This is, for instance, one idea that we came up with. Oh, yes. Thank you. So if you add one term here, mathematically you can show it. I haven't shown here, but we have done in some of our papers without going too much into depth, because that still needs work to be done. If you add this term here, it will add damping to the system. And what do we mean damping to the system? Damping means that, for instance, if you have a differential equation, x double dot plus x equals 0, the response is sinusoidal function. If you have x double dot plus x dot plus x equals 0, you have a sinusoidal which is exponentially going to 0. So this is damper. So by adding this, you will add damping to the system and make the oscillations going to 0 faster. So the system responses go to 0 faster. So this, to me, is one of the best ways that so far exists for adding damping to this one. Similar way is adding this term here. And then if you look at the literature, for instance, in the past 5 years, you can find tens of different approaches of damping. And I think a good work would be really reviewing these damper approaches and find out which one has what advantage. Because remember, these dampers should not interfere with the principal operation of the virtual synchronous machine. They should only make the responses going to zero faster, but should not interfere with other functions in terms of real power, reactive power, frequency, magnitude. So I think some of the publications out there, I realized they did not consider this, these points, these fine points. Anyway, so I think we can stop here and then continue in like 10:45.